So in this video we're going to talk about switching forms in the Fourier series. In the last video we looked at this triangle wave function and we were able to integrate to find the Fourier coefficients for exponential form. Now exponential form is when we have this e to the j omega naught nt. And after doing all the work we were able to find that for even multiples of n it came out to be 0, and for odd multiples of n, we found that it was 4 over n squared pi squared. So now we want to be able to go from exponential form to either trigonometric or compact form. Trigonometric form is an infinite sum of cosines and sines, whereas compact form is just an infinite sum of just cosines, but instead of just having the amplitude weighting, c sub n, it also has an angle phase shift, theta sub n. So in order to find these c sub n's, we have to take twice the magnitude of our f of n, where we kind of do it the same way we would with finding magnitude and phase angles of phasors. So if our f of n is written as in the form of a plus j times b, our magnitude is just going to come out to be the square root of a squared plus b squared. So in this case, the magnitude of f of n, since it's purely real and there's no imaginary numbers in there, it's just going to be equal to the square root of 4 over n squared pi squared quantity squared, which just comes out to be 4 over n squared pi squared. Now to find c sub n, all we really have to do is just multiply this by 2 to take twice the magnitude, which comes out to be 8 over n squared pi squared. Now to find these theta sub n's, we have to take the angle of f of n. And if we were treating it once again in this a plus jb format, the rectangular form, all we'd have to do to find the angle is to take the arctangent of b over a. So in this case, again, it's only real, so our b is equal to 0. So in order to find theta sub n, we just take arctangent of 0, which just equals 0. Now, to go to trigonometric form, what we would do is for the a sub n values in front of the cosines, we would take f sub n plus f sub minus n. And in order to find f sub minus n, you just plug in a negative n anywhere you see a n in your equation. So f sub n is just the same, 4 over n squared pi squared, and f of minus n is equal to 4 over negative n squared pi squared. And because it's squared in the denominator, it just comes out to be the same exact thing as f of n, which is 4 over n squared pi squared. So to find our a sub n values, we were just going to add these two together. So a sub n equals 8 over n squared pi squared. Now our b sub n values, if we look back up at this table, which is in your textbook and on the course website, your b sub n is just going to be j times f of n minus f of minus n. And in this case, since they're the same, f of n minus f of minus n is going to be equal to 0. So your b sub n values is just going to be equal to 0. And for this particular example, the compact form and the trigonometric form is actually the same, since it's only made up of cosines. So it's just kind of a neat little example. And another trick you could use is that since the function we were looking at was originally an even function, and that means that it's symmetric about the origin, that means that it's only going to be made out of cosines. And if it were an odd function, it'd only be made out of sines. So right off the bat, you can know for this particular one, your b sub n values are all going to be 0. So one important thing to mention is that all the previous calculations we did were for when n was odd, because our f of n only has non-zero values for odd integers. So whenever it's even, it's just going to be 0. So our final answer for a of n is just going to be 0 for n even, and 8 over n squared pi squared for n odd. Now our b sub n for both these cases is just going to be 0. So we can just say b sub n is 0. Now our c of n is going to be just like a of n. It's going to be 0 for n even, and 8 over n squared pi squared for n odd. And just like b sub n, our theta sub n is going to be 0 in both cases. Now to find these first terms, these a sub 0 over 2 and these c sub 0 over 2, it's the same way we would do to find f of 0. And to do that, we would just find the average value of the function, which the way to do that is you say 1 over the period times the integral over the period of f of t, whatever function we were talking about or that you had in mind. In this case, our f of t is just that triangle pulse, which looked a little something like this. So our function has a period of 2 because it goes from -1 to 1 before it repeats. And between -1 and 0, it has this value of 1 plus t, and then from 0 to 1, it's 1 minus t, because it's just these two line segments. So in order to do our integral, we can say 1 over 2, because that's our period. The integral from -1 to 1, f of t dt. And since our f of t is piecewise and different over this range, we have to split up our integral. So that just becomes 1/2 times the integral from -1 to 0 of 1 plus t dt plus the integral from 0 to 1, 1 minus t dt. So now when we integrate, we get 1/2 of t plus t squared over 2, evaluated from -1 to 0, plus t minus t squared over 2, evaluated from 0 to 1. So we found that the average value is 1/2. So a sub 0 over 2 equals c sub 0 over 2, which equals f sub 0, which equals 1/2. And that's how we find this DC offset, is what a lot of the professors will call it, which is just the average value of the function.